Okay, so this video is going to help you understand what continuous functions are and functions that are discontinuous. Alright, so just to recall, a continuous function is a function where you can draw like a sine graph and you'll never have to lift your pencil to draw it out. But if a discontinuous function happens, it's going to have one of these three vocabulary words happen. You could have a hole in the graph, and that's when algebraically when you have a 0 divided by a 0 happen. And if you take a look at this function here, it actually does have a hole in the graph right at 2 comma, it looks like about 1.5, but it's hard to tell. But this hole in the graph is creating a 0 up top because you have 2 squared plus 2, which is 6, minus 6, which is 0, divided by 2 squared, which is 4. 4 minus 4 is 0. And you can't divide by 0, so there's definitely a problem there. So a hole in the graph is a discontinuity. A vertical asymptote is also a discontinuity. And if you look, this graph also has a vertical asymptote discontinuity at -2. So it has two problems. It's got a hole at 2, and it's got a vertical asymptote at -2. Piecewise functions can have a jump in them. So something that we've done in a different video, if a function goes maybe down with a hole in it here, and then maybe an open circle here going that way, and let's say that this happens at 1, you'd say that this function has a jump discontinuity at x equals 1. But since we're dealing with a rational function, which is a division function or a quotient function, it cannot have a jump in it. So we will leave that for a different scenario. But for right now, let's take a look at your graphing calculator and how you can kind of see some of this happen. So I typed in the function right here in the y1. Let's hit graph. And so you can see easily the -2 vertical asymptote, but you cannot tell at 2 that there's a hole here. But what you can do with this, with your table is to see what's going on with the function value at 2. So if you look at 2, you could see there's an error message going on right here, so you know that there's a problem. When x equals 2, there's nothing happening. So you know that it's an issue, you know it's a discontinuity, and to algebraically figure these things out, the hole in the graph is always going to factor out. So again, it's going to create the 0 divided by 0, but when you factor this top to x plus 3 and x minus 2, the bottom factors to x plus 2, x minus 2, these x minus 2's can factor out. That leaves you with a different function. Now technically, this function here doesn't really equal this function here, so you should use something like an arrow, because this doesn't technically equal that. When you take a look at the graph, they will look like they're the same thing. So like this function here is discontinuous 2 places, at x equals -2 and +2. But if you reduce the function down, like canceling out this x minus 2, x minus 2, again, that's where the hole is at. Like if you put a 2 here for this x, that'll be 2 minus 2 and 2 minus 2, or 0 over 0. If you cancel that out, you're left with a function that doesn't have a hole in it. So if we go back to the calculator, turn on the red y2 graph like this, then click graph, you'll see it's going to look exactly like the original graph, except that this one does not have a hole in it at x equals 2. This one you could go back to the table and see when we're at x equals 2, you get this value of 5/4 or 1.25. So that will tell you right here that the hole is at 2 comma 1.25. That's where the hole is at. But what you are going to do for some practice is just to figure out where do the holes exist in these functions. So just get familiar with the vocabulary. Holes exist when you have a 0 divided by 0 in the function. A vertical asymptote is going to happen when you have a non-zero divided by 0. So that would be like right here. If we put negative 2 into this, it'd be negative 2 plus 3, which is a 1. Negative 2 plus 2 is a 0. So the vertical asymptotes are going to happen if any non-zero divided by 0 occurs, or a hole in the graph is going to occur when you have a 0 divided by 0. So we'll take a look at some practice. Alright, so for this first example right here in problem 42a, we see that x being a 0 is definitely a problem. We can tell it's a discontinuity because it's making the denominator 0 and we cannot divide by 0. But if we have a 2 over 0, that's our non-zero over 0 situation. So this is a vertical asymptote in this function. And you can see right here when x equals 0, we have a vertical asymptote happening in the function. So that would be our answer. There would be no holes in this particular function because at no x is it ever a 0 over 0. So this one has no holes, but it does have a vertical asymptote at x equals 0. So it says right here, find the x value of the holes, if any. So A would be no holes. Alright, for B, let me type this in the calculator, so just let me pause the video. Okay, so I typed in the function. You can see right here I've got 3x times x minus 5 divided by x minus 5. Click graph. We're going to take a look at it. It looks completely linear, but if you look at the table, you're going to see this error message happening at 5. So we have 5 error. And that is because if we try and throw 5 into this function right here, we're going to have a 3 times 5, or 15, times 5 minus 5, 0, over 5 minus 0, 0, which is really 0 over 0, which means that there's a hole in the graph at x equals 5. So you can't really see it on the screen. So when we go to x equals 5, 1, 2, 3, 4, 5, it's actually here. It would be a little bit off of the screen. So that's why if we go to our window, make the y maximum a little bit higher so we can see it, maybe like 25. Then go back to the graph. And then we'll see it 1, 2, 3, 4, 5. You still won't be able to see it with your eye. Well, sometimes on this particular calculator, because I'm using a computer, you can see this little break. Most calculators are not going to be able to see that break, but there is this little missing piece right here. But most handheld calculators are not going to be able to show that. So the only way to tell is to be able to use some algebra skills and factor this out. So that's why the x minus 5 can cancel out. This function reduces to 3x, and that's kind of what you're looking at. This is the equation 3x. But the original function is going to have a hole at x equals 5 because it's forcing the f of x to be 0 over 0 at that place. And that's why if you try to get a function value at 5, it's not going to give you it. Or if you try right on the home screen, if you try the alpha trace y1 of 5, it'll always give you an error message. Say right here, you cannot divide by 0. And we could hit go to. And the only way to fix this is to type in the function 3x instead. So that's why if you just type in 3x and then you plug in 5, you'll be able to tell where the hole is actually at. It's at 5 comma 3 times 5, or 15. Okay, but let's take a look at one more so you kind of see what's going on here. This one has a discontinuity at x equals negative 2. And now you have to see, is it a hole or is it a vertical asymptote right here? Well, if we take the top and we factor it to x plus 2, x minus 2, and the bottom is x plus 2, we can take these x plus 2's, reduce this out, and we're left with this function right here. So if we make this a negative 2 right here, you can see that this function will go 0 over 0 when x is a negative 2. So this is a hole and not a vertical asymptote. So again, this is now on page 19 of the summer packet. You can see that this function here has two vertical asymptotes happening. We've got a vertical asymptote at 1, and we've got another vertical asymptote at 3. And again, if you read this, you can see vertical asymptotes as the x gets closer to 1 from the left side of the 1, the y value is just getting bigger. That's why it says it's approaching positive infinity. We're just skyrocketing up, up, up. Like the y value, the closer we get to 1, the closer this number is getting to basically infinity. It's just going up forever. If we're to the right side of 1, like 1.1, like the y value is just getting bigger and bigger and bigger and bigger and bigger, going to positive infinity, and that's what happens. So let me type this in the calculator and you can see what I'm talking about. Alright, so I typed it in, and if you look, this is the picture that we have going on, and if we try to take a look at the table here, and we type in 1, you'll see you're going to get an error message. This is going to be impossible because we have a discontinuity. We have a vertical asymptote discontinuity. So if you go close to the 1, like 0.9, the value is getting pretty big. And if you go even closer to the vertical asymptote, like 0.999, the value gets even bigger. And the closer you get to 1, the bigger it will get because it's going up to infinity like this. And same thing from the other side of 1, like 1.001. The value will be just also huge. It's like 499,000. Bigger, bigger, bigger. So again, that's just what's happening next to a vertical asymptote. The function's either getting enormously big, or like over here, like at 2.9, we type in 2.99, getting close to this other vertical asymptote at 3, the number will be huge but negative, and the closer we get to that 3, like this, the bigger the number is getting in a negative way. So like the bigger or closer we get to the 3 from this side, the bigger but negative the number is going to get. And if we type in like 3.1, it's going to be a huge number, and getting bigger the closer we get to 3 from the other side. So if we go 3.01, should be getting bigger than that, or 3.001 should be even bigger, and so on and so on. So that's what a vertical asymptote does. It gets either infinitely big or infinitely small. So if we take a look at these examples here, we look at the bottom. X equals 0 is our problem, and it's not a 0 over 0 situation, so right there we can tell that x equals 0 is a vertical asymptote. Over here in the next problem, x equals 5 is a problem because it's making the denominator 0. It's 1 over 0 in that case, so again, it's not a hole, it's a vertical asymptote. Remember, holes are 0 divided by 0. This one here is going to have two problems. X equals positive 2 and negative 2, neither of which are going to create a 0 over 0. So these are both vertical asymptotes for that problem. This one, since the bottom factors, so the top is an x plus 2, the bottom is an x plus 2, and x minus 2. The x plus 2's can cancel out, leaving this function reduced to that. Again, you have two discontinuities. X equals 2 is a problem, and x equals negative 2 is a problem. However, the 2, if we put it here, is going to create a 1 over 0. So that's not 0 over 0. So that's why this one is the vertical asymptote. This one, if we make negative 2 go back to the original, negative 2 plus 2 is 0. Negative 2 squared minus 4 is 0. So anytime you create a 0 over 0, that's the little hole in the graph. And you could see it with a computer or see it with a really good calculator. But the x equals 2 is making the vertical asymptote discontinuity. X equals negative 2 is creating the hole in the graph.